Now that you know the difference between Cartesian space and configuration space, that is, Cartesian space is an XYZ space that represents locations in the real world, and configuration space is a theta 1, theta 2, theta 3, or perhaps with some D's in there, depending upon whether your joints are revolute or prismatic. We can use this difference between the Cartesian space and the configuration space to help us plan motion. We're going to use a simple 7-step process to plan our motions using Cartesian space and configuration space. Step 1 is to find your manipulator's workspace in the configuration space. You do this following the procedure that I showed in the previous video, and I'll show a couple of examples in the next video. The reason why we do this in configuration space instead of Cartesian space is because it's much easier to find the workspace in configuration space rather than Cartesian. Step 2 is to find the start and end points for the particular move you're trying to plan in Cartesian space. The reason why we do this in Cartesian space is because that's the space in which our real-world points are defined. So for example, you might know the location of a point or an object that you want to pick up with the manipulator, and you might know the location where you want to drop that object off. These points are defined in Cartesian XYZ space. Step 3 is to transform those start and end points which you defined in Cartesian space over to configuration space. You do this by using the inverse kinematics. The reason why you want to do this is because you need to make sure that those points are in the workspace. And remember that you have found the workspace in configuration space. So you need to make sure that these start and end points, which you defined in Cartesian space, do in fact lie within the space that you've identified as your workspace in the configuration space. If not, you want to stop here because your robot is not able to perform the task that you're trying to get it to perform. If these points are within the workspace, we then have an option for which step we go to next. There are a couple of possibilities for what we're trying to do. One possibility is that at this point you know the desired path that you would like the end effector to take in the Cartesian frame. For example, maybe you're trying to do a robotic painting operation and you know the path that follows the contour of the car, and you know this path in Cartesian space because, of course, the car is also in Cartesian space. Or perhaps you're doing a pick-and-place operation and you know that you want the end effector to follow, say, a parabolic path between the pickup location and the drop-off location. The other case is the possibility that you do not have a specific desired path in mind in Cartesian coordinates. You just want the move to be efficient. That is, you want to make the move between point A and point B, the start and end points, with as little effort or as little power consumption as possible. We'll look at both of these possibilities. And we'll start with the possibility on the left, the case where you know the desired path in Cartesian coordinates. In this case, our step 4 will be to plot the motion in Cartesian coordinates. In other words, we know the desired path in the Cartesian frame, and so we go ahead and plot the desired path in that Cartesian frame. Next, we're going to take that path that we've plotted and we're going to break it up into little pieces. We're going to segment or interpolate the path into equal segments. So that the distance between each of the points you identify along the path are an equal length. So for example, let's suppose that you know that the start location is right here and the end location is right there, and you want to follow a roughly parabolic path between these 2 points. In step 5, I'm going to identify the points along this parabolic path that are equal distance apart from each other. And this is equal distance of the arc length or the path length. Finally, for step 6, we're going to convert these interpolated points back from the Cartesian frame to the configuration coordinates. So we convert the interpolated points back to configuration space, and we do this once again by using the inverse kinematics. I'm going to stop here and follow along the other possibility where we only want to be efficient, because both of these approaches have a step 7 and it's the same step 7. The last step, which is the same for both approaches, is to send commands from the configuration space to the servos. In other words, we take each of those interpolated points, which we've now converted back to configuration space, and those are the commands that we send to the servos. Remember that in the configuration space, we have all of the points that we want the end effector to be in expressed in terms of the joint variables, the thetas or the d's. So those points can be directly sent to our actuators. Now let's go back up to step 4 and suppose that instead of knowing the desired path in Cartesian coordinates, we just want the move to be efficient. We probably all know that the shortest distance between 2 points is a straight line, and so we would expect that our most efficient move would be a straight line. The question is, should we use a straight line in the Cartesian space, or should we use a straight line in coordinate space? Or rather, configuration space. I'm showing here an image from the supplemental reading provided for today, showing the kinds of motions that are necessary for this articulated manipulator to follow a straight line path in Cartesian space. This picture shows a path between points A and B that is a straight line in Cartesian space. However, it shows that in order to follow this path, angle changes are required in all of the angles or all of the revolute joints that this robot has. This angle changes, this one changes, and so does this one. And so this task of following the straight line in Cartesian space is actually a fairly complicated motion required of this robot. When we want to simply be efficient in the paths that we plan for the motion of our manipulator, we want to plan motions that are a straight line in configuration space, not in Cartesian space. However, we have to be aware that a straight line in configuration space is not necessarily a straight line in Cartesian space. That is, the end effector of our manipulator will not necessarily move in a straight line when we follow a path that is a straight line in configuration space. We can see that this is true by going back to look at our simple 1 degree of freedom manipulator. In this case, when this manipulator moves in a straight line in configuration space, it will move this one angle a certain distance. This motion from angle 1 to angle 2 is a straight line in configuration space. However, the motion of the end effector is not a straight line in this case. It is a circular arc. This motion that I've drawn here would look like this in configuration space. Here we have theta 1. This motion is from one point on theta 1 to another point on theta 1, traveling between all of the angles from the first angle to the second angle. So this motion is a straight line in configuration space. However, in Cartesian space, the motion of the end effector is a circular arc, not a straight line. Because of this, when we're making motions in order to be efficient by moving in straight lines in configuration space, we want to make sure that the actual Cartesian movement of the end effector is an acceptable kind of a motion. The way that we do that is by moving on to step 5, which is once again to segment or interpolate the path. However, in this case, we're segmenting or interpolating the path in configuration space, not in Cartesian space as we were doing in the other method. Once this path has been segmented or interpolated, we then go on to step 6, which is to convert our interpolated points back to Cartesian space. And remember that the way that we convert points to Cartesian from configuration space is to use the forward kinematics. We do this so that we can make sure that the path in Cartesian space is acceptable. We'll go into this idea of making sure that the path is acceptable a little bit more in detail in the next set of videos for the next day when we look at collision avoidance. In any case, the last step of this process is the same as the last step of the previous process, which is that we send the commands from the configuration to the servos. We only did this conversion of the points to Cartesian so that we could make sure that the path is acceptable. The points that we actually send as commands to the servos are still the points that are in configuration space, since that is the space that tells us the values of each of the joint variables. In the last video of this series, I'm going to show you a couple of examples for how we do this for a couple of different kinds of manipulation.